Yes, thank you very much, Mauricio. And thank you for the invitation to present some of this. Yeah, so I'll talk about neutrinos in the early universe. And I know that Olga Mena has already covered quite a lot about neutrinos in cosmology, so I'll focus on a small part of what she talked about. But let me first draw sort of the broad lines. We believe that the universe started with a period of inflation where the universe expanded very rapidly. Then it was followed by the electric phase transition, the QCD phase transition. And then we get down to temperatures around a few MeV, where we have neutrino decoupling, electron-positron annihilation, and nuclear synthesis. Then at much lower temperatures of about an EV, we have recombination and also the formation of the cosmological microwave background that we can observe today. And after that, we also have large scale structure formation of stars, and eventually the Earth and us. But today, I'll focus on these 3 points. So neutrino decoupling, electron-positron annihilation, and a little bit on nuclear synthesis. So neutrino decoupling, very briefly, takes place when the weak interaction rate becomes smaller than the Hubble expansion rate. And then reactions of this type, where neutrinos scatter on electrons, stop being efficient at keeping the neutrino coupled to the electron-photon plasma. At slightly lower temperature, so this takes place at about 1 MeV, at slightly lower temperature, when the electrons and positrons become non-relativistic, we have what we call electron-positron annihilation. So electrons and positrons produce 2 photons and vice versa. This, of course, this reaction takes place at all temperatures. But what happens when the electrons and positrons become non-relativistic is that it's shifted towards the photon side of the equilibrium. So we lose all of the electrons and positrons in the plasma. There's, of course, also electrons and positrons producing neutrinos and antineutrinos. But since we are below at the temperature of neutrino decoupling, this process is much rarer than the production of photons. And then at a few hundred or 100 keV and below, we have nuclear synthesis, or Big Bang nuclear synthesis, as it's also called, where we produce the light element abundances. So here, neutrons and protons combine and produce mostly helium and also deuterium and helium-3 and lithium. So when we look at the things that we can observe from the early universe, one of the most interesting things are the light element abundances themselves. And the reason that this is interesting from a neutrino point of view is that neutrinos help set the ratio of protons to neutrons before Big Bang nuclear synthesis, and hence, since at 0th order, what Big Bang nuclear synthesis does is to take all of the neutrons and put them into helium. So if we change the ratio of neutrons to protons by changing neutrino physics, then we also change the helium abundance. So when we go on and measure helium and deuterium, we can constrain physics of the early universe and also neutrino physics. What you see in the figure here are a comparison of theoretical calculation and measurements. The purple is the theoretical calculation and the yellow are the measurements. The blue one is from CMB, and we won't consider that right now. So for helium, we have the helium mass fraction YP here. For deuterium, we have the relative abundance of deuterium and hydrogen, and these both show great agreement between observation and theory. For helium-3, we do not have a measurement, and for lithium, the measurement and theory do not agree very well at all. This is what's called the lithium problem, and it's very interesting on its own, but I'll not go more into details of it today. So another observable is what we call ineffective. I know that Olga also introduced this, but let me just repeat it for clarity. So the energy density of radiation in the early universe consists of the energy density of photons, that of neutrinos, and any beyond standard model contribution. And we can write this in terms of course, the photon energy density, and then this parameter ineffective, where there are some funny constants in front. These constants mean that if we take the simplest calculation of ineffective, what is called the instantaneous decoupling approximation, then we get that the number of effective number of relativistic neutrino species is equal to 3. However, if one performs a more detailed calculation, then the actual number is 3.044. The value of ineffective affects both BBN and also the cosmological microwave background, because it changes how the universe evolves simply because of the contribution to the total energy density of the universe. So using only CMB, you can get a constraint on the number of neutrino species. And also from BBN alone, you can get a constraint, and these can also be combined. The green curves here are what is seen on the right figure. And we can see that if we combine all of these measurements, what is found is that 3 is very well compatible with the observations, and both 2 and 4 are excluded at very high significance. So how do we get to this number, 3.044? So there are a number of corrections to the 3.0. The leading one is due to the non-zero electron mass. And then there are contributions from finite temperature QED effects, non-instantaneous decoupling of the neutrino, and also from flavor oscillations. And I'll try to describe these in a bit more details than Olga did early on the week. Good. So let's start with the correction from the non-zero electron mass. So in order to do this, we go back to how to treat the neutrinos in the simplest case. So in the instantaneous decoupling approximation, we can look at the entropy density. This is one of Olga's slides, so hopefully you have seen it before. Otherwise, I'll go very quickly through it. We consider entropy and use that entropy is conserved, co-moving entropy is conserved. The entropy per boson is given by this number, and for each fermion by this number. Then we can set up the total entropy before and after neutrino decoupling, and before and after electron-positron annihilation. And this gives this ratio of T nu to T gamma, which is 4 divided by 11 to the 1/3. If we now want to include the effect of non-zero electron mass, we can basically set up the same argument. So we assume entropy conservation between a scale factor A1 and A2, both for electrons and positrons, and also for neutrinos. If we then choose A1 to be at the decoupling temperature and A2 to be well after electron-positron annihilations, then we get these contributions to the entropy densities. And then in addition, we get a contribution to the entropy from the non-zero electron mass, and that is only for electrons and photons at high temperature, so at the neutrino decoupling. This number can be calculated simply by solving this integral numerically, and then we can subtract the approximation where the electron mass is assumed to be 0, and we get this quite small number, which can be translated to the change in effective. And then we get these 0.04 change in the effective number of neutrinos. So this calculation is actually reasonably simple. We can include a correction, propagate it through the equations, and then we get a correction which explains the majority of the 3.044. The next correction that we look at is the finite temperature QED correction. If we assume that the electrons and photons constitute an ideal gas, then they are not interacting at all. But in reality, there's an interaction between them. And that means that the kinetic energy is modified. They get efficient masses if we want to use a quasi-particle picture. And the potential energy also get an interaction contribution. So in the end, this can be accounted for by modifying the QED equation of state. If we want to do this in a slightly more formal way, we can go and use our tools from statistical mechanics. So we can use the grand partition function, Z, and then from Z, we can compute the pressure, the energy density, and the entropy density to different orders. So if we expand in powers of the elementary charge here, we get that the 0th order is present. There's no first order, but then there's a second order and a third order correction to the 0th order term here. And for each of these, you can compute the pressure, energy density, and entropy density. And these are just standard formulas that I have put here. Good. So if we look at the 0th order term, then we get the equations for an ideal gas. So that's sort of the base. Then higher order corrections come from interaction between photons and electrons. Those are second order corrections. And then there are some plasmon effects where the photons get an effective mass. And these give third order corrections to the equation of state. So if we take an example, we can look at pressure to second order, and then we get the expression that I show here. So this looks maybe slightly nasty, and people have not actually been using this until recently, but instead they have used an alternative way of accounting for the finite temperature effects. And that is what is called the quasi-particle picture. So instead of including this kind of integrals in your calculation, you simply shift the energies of the photons and the electrons by giving them an effective mass. This is, in some sense, much simpler, and it works very well for transport equations, but for bulk properties, there's a double counting. So you can see this basically as if you have one particle, then it affects the other, and then you go to the other particle and look, and then that's also affected by the one. But this actually means that you have counted the interaction twice. So you need to be very careful about that when you do this quasi-particle treatment. Also, this picture cannot account for plasmons or other collective excitations, so it's only accurate to the second order correction and cannot go further than that. Good. Yeah, so when you put this into your equations, you get this change in effective of 0.01. The next effect that I would like to talk about is the non-instantaneous decoupling. So instantaneous decoupling means that we assume that the neutrinos decouple exactly at one single temperature, and that then they do not interact at all after that point. That is not actually true, because electrons and positrons do produce a few neutrinos even after that. And this means that there will be a shift in the high energy tail of the neutrinos. And also high energy neutrinos can annihilate to electrons and positrons. So there's still, especially for the high energy neutrinos, an effect there. the way to account for this is to get the exact evolution of the photon temperature. You could do that by solving the Friedmann equation and the continuity equation. And then one also has to follow the distribution function of the neutrinos accurately. This is done by solving a Boltzmann equation. So F is the distribution function for the neutrinos, and we of course need the time derivative. The second term here accounts for the expansion of the universe. And then on the right-hand side, we have a collision term. So if we take an example of two particles going to two particles, then the collision term has the form that you see down here. So there's a phase space integral, which integrates over 9 dimensions, so 3 particles and 3 momenta for each. Then there's conservation of energy and momentum. There's a matrix element which contains the particle physics details of the given reaction. And then there are all of these distribution functions that accounts for Pauli blocking and, of course, production and loss of particles, of the different particles. So this collision term looks quite complicated, and it's also numerically quite expensive to evaluate. One can reduce the integrals here from 9 to only 2 integrals, but even then it's a comparatively expensive computation to evaluate this collision term every time. So that is one of the things from a practical point of view that one faces when dealing with these things, that whenever you encounter these collision terms, you need to consider if you can actually evaluate them in all detail. So if you do this calculation, then you get another shift of the value of ineffective, which is also noticeable. So if we go back to our table now, we have covered the first 3 corrections, and I'll skip the 4th one. That's another finite temperature QED correction, and then jump to the flavor oscillations. So as Shashank introduced, we can treat flavor oscillations with these density matrices. And that means that we need to replace the distribution functions F by density matrices. And the density matrices basically still contain the distribution functions on the diagonal for electron neutrinos, muon neutrinos, and tau neutrinos. But then on the off diagonal, we have these coherence terms that describe how large the overlap between different flavors is. So when we want to account for this in our equation, we need to combine the equations for oscillations that Shashank presented before with the Boltzmann equation. So from the Boltzmann equation, okay, we of course have the time derivative. We want to know how the density matrix evolves in time. Then from the Boltzmann equation, we have the expansion of the universe that we must account for. And we have a collision term that describes how the neutrinos interact incoherently with the background. And then the oscillations are taken into account by this commutator between the Hamiltonian and the density matrix. That is equivalent to the Schrödinger equation that Shashank showed before. So the Hamiltonian has the form here. There's a vacuum term, which is consists of the mass matrix of the neutrinos rotated by the PMNS matrix, and divided by the momentum. This just accounts for vacuum oscillations. Then there's this asymmetric neutrino-neutrino term that Shashank also introduced. So I'll leave that for a moment. And then we have this asymmetric matter term. So in contrast to the usual matter term, which depends on the number of electrons minus the number of positrons, this one depends on the sum of the electron density and positron density. The thing is that in the early universe, we have almost equal amounts of electrons and positrons, so the difference is going to be approximately 0. This term is then a higher order term, and it's suppressed by the mass of the W boson squared compared to the usual matter term. But still, this turns out to be the dominant matter term in the early universe. So if we take this Hamiltonian and put it into our quantum kinetic equation, and modify the collision term also to take into account that we now have matrices and not just scalar functions, then we can figure out how large a correction to ineffective we get. The result is this 0.3 zeros and a 5. So we are getting towards the details now. The reason that it's positive is that oscillations in general tend to equilibrate different flavors. So when muons and tau neutrinos only interact via a neutral current, and electron neutrinos interact via both a neutral current and charge current, then when the oscillations remove some of the electron neutrinos, then they are basically making room for more electron neutrinos to be produced through the charge current from electrons and positrons. And that means that we get a slightly higher value of ineffective. So if one considers the variation of the mixing parameters, here we have the mass squared difference and the sine squared of theta. And on the y-axis, we have the value of ineffective. Then let's focus on the mixing angle. You can see that the dark blue is theta 1,3, and that is measured very well in here. The light blue is theta 2,3, which is not measured as well, but also doesn't change the result much. And then we have the theta 1,2, which is measured here, indicated by the shaded region. And the red line here indicates the theoretical prediction of ineffective with those different mixing parameters. So there's actually an uncertainty since you can see that there's a slope for the red line here. And this is a significant part of the uncertainty that in the end is quoted on ineffective. However, all of this calculation is done without the neutrino-neutrino term. So if we have a look at this was the neutrino-neutrino term. Then we can try to do a calculation where we include it and not neglect it. The problem is, as Shashank said, the neutrino-neutrino term is very rich in terms of phenomenology. So it can actually give rise to a lot of features in the result that makes the computation much harder. So it's not just another term that you also add a lot of physics and complications to your calculation by including it. Good. So if we look at the results here, this is for a 2 neutrino oscillation framework. We have an electron neutrino and an X neutrino, and the X neutrino represents both muon and tau neutrinos. Then you can see that for inverted mass ordering in an isotropic universe, if we do not include the neutrino-neutrino term, then we get the black result here, the black line here. On the y-axis, we have the normalized number density. And for the X neutrino, we get the dashed line down here. And then when we include the neutrino-neutrino term, these two are pushed towards each other. There's some flavor equilibration taking place. And this will also mean that we expect the ineffective to be a little bit higher. For normal mass ordering, nothing is really happening here. But this ends up coming down to the assumption of an isotropic universe. So it turns out that if we break isotropy, we can actually change these results a bit. So let me try to illustrate with a bit of gymnastics. If we assume that we have an isotropic universe where neutrinos traveling in one direction and the other direction do exactly the same, then they oscillate together. Another possibility, if we do not assume isotropy, is that they oscillate out of phase. So by relaxing the assumption of isotropy, we end up with more solutions that can be realized. And this is also what we find. Here are some of the details of the model that I will talk about. We still assume a homogeneous universe. We use this 2-neutrino oscillation framework, and we approximate the collision term because evaluating it in full is too hard numerically. And then we use two directions, so only 2 angle bins, in order to model the anisotropy of the universe. When we analyze this model with a stability analysis from a linear point of view, we find the growth rate on the y-axis here. And if we start with the dashed line here, that is inverted mass ordering in an isotropic universe, or with isotropic initial conditions, I should say. And here you can see that there's a growth rate here, which is non-zero, and that means that that kind of solutions will be there. We will have an instability of the neutrino-neutrino term in this case. However, for normal mass ordering, you can see that it's only the anisotropic solution that is present here. So if we have isotropic initial conditions for normal mass ordering, then the neutrino-neutrino term is not going to lead to any unstable solutions. But we expect that with the anisotropic initial condition, we will get it. So let's look at the results. For the inverted mass ordering, it looks basically the same as it did for the isotropic initial conditions. But for normal mass ordering, you can see that now both left and right moving neutrinos have moved away from the no neutrino-neutrino line here. And also they've moved apart. So we actually have that neutrinos traveling left and traveling right are doing different things in this case. Of course, the scale here is quite small, so it's not a huge effect, but it's phenomenologically, it's very interesting that we have this breaking of isotropy in the early universe for normal mass ordering. If we get back to the effect on an effective, the model that I have shown here give an effective of 3.0460 if we have no oscillations. That's not accurate at all. The model has a lot of assumptions, but it's quite precise. So we can look at differences between different models with different assumptions. So if we compare the no oscillation result to the isotropic result, we get a shift of 0.001, so 10 to the minus 4 times 1. If we then allow for anisotropy, we get a result that is 5 times larger. So anisotropic oscillations can actually shift the correction here for flavor oscillations quite a bit. One cannot take these the number from these two tables and compare them directly because our model is much simplified, and the other model doesn't contain the neutrino-neutrino term. But it indicates that maybe the error here at least is a bit underestimated, and we could have a small shift in an effective. And then a very interesting perspective is also beyond standard model physics, where sterile neutrinos and low temperature reheating in particular could see even larger effects because these two scenarios both tend to give rise to non-equilibrium neutrino distributions at low temperatures, so at MeV temperatures. And this could give rise to large anisotropic oscillations. So with this, I would like to summarize that an effective is a very powerful probe of both standard model, also standard beyond standard model physics. The standard model value is 3.044, and these corrections beyond 3 come from the finite non-zero electron mass finite temperature QED, the non-instantaneous decoupling from neutrino oscillations, and we also saw how neutrino oscillations in the early universe can be both anisotropic, and we expect them also to be inhomogeneous, but we do not have the numerical calculation for that case yet. So thank you very much for your attention.
Thank you, Rasmus. Thank you for the detailed breakdown of how we get this NF. Do we have any question in the audience? I actually have one thing, maybe I can start. That wasn't fully clear with me. When you talk about early universe anisotropy, I wasn't sure if it meant you're putting the anisotropy yourself by hand and see how the flavor evolution goes, or if the evolution itself is created by anisotropy.
Yeah. So, okay, let's start with this one. So what I show here is the growth rate, and that means that it's the exponential growth rate. And you can see that the growth rate is normalized to the Hubble expansion rate, and the numbers are huge. So this means that even if we put a tiny initial anisotropy in the system, that very small initial anisotropy will grow to order 1 very, very rapidly once you enter this temperature range with the conditions that that allow for the instability, for the exponential growth to be present.
I see.
So I put a tiny initial seed, and then the dynamics of the system amplifies that to order 1 effects. So here, in both these cases, I've put an initial seed of 10⁻⁻15, and in the inverted mass ordering case, you can see that there's basically nothing changed, but for normal mass ordering, that initial seed has been amplified a lot.
And I guess that the size of the seed doesn't matter much.
No,
as long as it's small.
It doesn't. I mean, if you make it small enough, eventually you might hit a numerical limit of how small numbers you can track.
Mm-hmm.
But other than that, it can be very, very, very small.
Okay, that clears it up. Thank you. Marcus has a question.
Nice talk, Rasmus. On the previous plot where you show the growth rate, there seems to be some sort of, so something happens around 5 mega electron volt where you have like this dip. Is this somehow related to physical dimensions or energy scales? Yes, here in the problem?
Indeed. So what happens at 5 MeV is that if we go back to the Hamiltonian, at 5 MeV, the symmetric matter term stops being dominant and the vacuum term takes over. And that's also why the symmetry properties of the inverted mass ordering changes. At higher temperatures, the anisotropic mode for the inverted mass ordering is the unstable one, or the exponentially growing one. And at lower temperatures, it's the isotropic one that is, is the exponentially growing one. So there's a very good reason why we have this feature at 5 MeV.
Nice, thanks. And so when you say meta terms, can you remind me, are these also then the electrons that you need to consider, or is this at these high temperatures also other species?
So the temperatures are not that high. So this plot goes up to 20 MeV. So at this temperature, it's only the electron and positron that you need to include.
And positrons as well, yeah.
Yeah.
Okay, thank you.
So I think we can transition to our discussion.